Hello, today we're going to try and look at general relativity, and we're going to start from scratch, and we'll only be able to look at the very early basics of general relativity, which gets quite complicated after a while. But in our usual way, we'll try and start simply. We're going to start with Newton's law of gravitation. Newton said that if you have two masses, m1 and m2, then the force between them, which is the gravitational force, is equal to the mass 1 times mass 2 divided by the distance between them. So here's m1, here's m2, and here's the distance between them, r. Distance between them squared, times what is called Newton's gravitational constant. And that gravitational constant is 6.67 times 10 to the minus 11 Newtons metre squared kilogram to the minus 2, which sound like rather odd units, but they are necessary in order to convert a force which is measured in newtons to masses which are measured in kilograms and distances which are measured in metres. That's the reason for this conversion factor. Now, when we are standing on the Earth, here's the Earth, there's essentially R for our purposes, and here am I standing on the Earth. When I stand on the Earth, R is constant. My mass is m1 and the Earth's mass is m2. And so writing this, we get m1 m2 g over r squared. But m1 is my mass, m2 is the mass of the Earth, g is a constant, and r, of course, is a constant if I stay on the surface of the Earth. And so that term there is essentially a constant. The constant Earth mass, constant g, constant r because I'm on the surface. And therefore that becomes m1, which is my mass, times g, the force of gravity on the surface of the Earth. And g is very approximately 9.81 metres per second squared. And this means that when I stand on the surface of the Earth, I experience a force which is mass times the gravitational attraction. Why do I not fall through the Earth? Well, that is simply because the molecular structure of the Earth's surface, or the floorboards, or whatever I'm standing on, is stronger and is able to stop me from falling through it. So I don't actually move, but there is still a force acting on me. Now, this led Einstein to consider what was called the equivalence principle. And what he said was that if you were in a box, and that box was in free fall, in other words, it had been dropped out of an aeroplane, let's say, and it was falling towards the Earth under gravity G, inside that box you would feel weightless. You would float. If you had something in your hand and you let go of it, it would simply stay there, because it and the box are both falling to the Earth at the same rate. So there would be no relative movement, and you would feel weightless. On the other hand, if you were in outer space, well away from any other masses, and you were in the same box, you'd also feel weightless. And so Einstein said there was an equivalence between these two things. A person who's in a box in free fall in a gravitational field feels weightless, and a person who's in a box in outer space where there is no gravity feels weightless, and the two are equivalent. He went further. He said that if you were in a box on the Earth, actually standing on the Earth, so you're subjected to the gravitational attraction, even though it isn't strong enough to pull you through the Earth, that, he said, would be entirely equivalent to you being in a rocket which was accelerating with an acceleration that was equivalent to g. So here we are in our rocket. There is no experiment, Einstein said, that you could do that could distinguish whether you were stationary inside a box on the surface of the Earth being subjected to the force G, or whether you were being accelerated in outer space in a rocket with an acceleration g. They would appear to be equivalent. Now I should say this is not quite true because of what are called tidal forces. We know from the formula that we wrote down first of all that the force on you is dependent on the distance. And so in fact when you're on the Earth, the difference between the force on your head and the force on your feet is slightly different. Of course it's totally unnoticeable on the Earth, but the force on your head is slightly smaller than the force on your feet because your head is slightly further away, and therefore r squared in this formula is slightly larger, which means force will be slightly smaller. And so there is a difference in the force on your head and on your feet, and that's called a tidal force, and it would tend to stretch you, except that on the Earth it's so small it doesn't make much difference on you. But it does make a difference on the oceans. If this is the Earth, and this is the Moon, and here is, let's say, a mighty ocean, here is the Moon, and the gravitational attraction on this part of the ocean will be subject to that r, but the gravitational attraction on this part of the ocean is that r, and that's a bigger distance. So the force here will be less than the force here. And that causes the water to swell in this direction. And that's what causes tides. But why did Einstein think that someone standing stationary in a box on the Earth, subject to the gravitational attraction, was in exactly the same equivalent position as a person in outer space in a rocket, which was accelerating at g? Well, the reason is, let's consider a person who, on Earth, inside the box, drops something. Well, if you're on the Earth and you drop something, it will fall to the floor under the gravity that is pulling it down. What happens if you're in outer space in a rocket, accelerating at g? Well, if you drop something, you might say, well, there is no gravity, so it will stay where it is. But of course what will actually happen is that it will stay where it is, but the rocket will move forward because it is accelerating. And so this point which stays where it is becomes here. You, of course, are standing on the floor of the rocket, so you have no choice, you move forward with it. So what has happened? This object here, which you have dropped, has appeared to fall to the floor. It has in fact stayed still and you have moved forward. But in essence, it will appear to fall to the floor as if pulled downwards by a gravitational attraction in exactly the same way as this. And that is the equivalence principle.